When we look at the Sun from the Earth, the most obvious features we see on its surface are the dark spots we call sunspots. These appear to be small spots to our eyes, but in fact, they're around the size of a planet. Sunspots appear on the Sun's surface and can remain for days or weeks before disappearing. Following these across the surface was one of the first ways people were able to measure the Sun's spin. Sunspots are dark because they're cooler than the surrounding surface. Remember that the Sun is glowing because it's hot, around 5,800 Kelvin at the visible surface. The sunspots are cooler spots, though they're still quite hot by our standards, typically 3,000 to 4,000 Kelvin. Sunspots are caused by the Sun's magnetic field. In fact, they form in places where the Sun's magnetic field is strongest. The gas in the Sun is what we call a plasma. Many of the atoms have lost some or all of their electrons, so they have an electric charge. But charged atoms have trouble crossing magnetic field lines. They tend to be deflected by them instead. So when the Sun's magnetic field is especially concentrated near the surface, it can block the convection cells that carry heat from inside. With less heat coming up from below, the surface cools off and a sunspot forms. The Sun's magnetic field is constantly changing. It's generated by the flow of hot plasma inside the Sun, but over time it gets more and more tangled up by the flows near the surface. Over an 11-year cycle, the field gets increasingly complex until finally it simply cancels itself out. Then, slowly, a new field is generated inside the Sun and the cycle starts over. The more tangled up the Sun's magnetic field is, the more sunspots form. So we see the cycle of the Sun's magnetic field in the number of sunspots on the surface. When there's a large number of sunspots, we see many other signs of the Sun's magnetic field as well, including prominences, like the loop shown on the lower right, and flares, which are sudden releases of energy when tangled magnetic field lines snap. Before we look at exactly how the Sun generates its energy, we should say a little about the theory that explains why it works, the special theory of relativity. In 1905, when Albert Einstein published the special theory, he was an unknown patent clerk, third class, in Switzerland. However, he was trained in physics, and he had been working on trying out a new way of understanding how motion worked. This new model of motion was based on two simple ideas. First, the laws of physics are always the same, no matter how fast you go. This one had been around for a long time, and we saw this when we talked about Newton's first law of motion. Moving in a straight line at a constant speed is just like standing still. Second, we always observe the speed of light in a vacuum as the same, no matter how fast we're going. This was first observed in a series of experiments around the turn of the century, and it's where Einstein's relativity starts being very strange. Think about what this says. If I'm moving towards a light source at half the speed of light, I still measure the photons coming towards me at the speed of light, not 1.5 times the speed of light the way you might expect. To explain this bizarre observation, we can remember that speed is just distance divided by time. So maybe the problem is with our usual understanding of distance and time. Your textbook goes through the steps to explain how this changes our perception of time and space. However, I'd like to jump right to the effects, starting with how time changes. The first thing to appreciate with all of these effects is that they're most obvious at speeds that are a large fraction of the speed of light. That's why we don't treat special relativity as simple common sense. We don't often experience things moving fast enough to show the effects. However, we can observe them experimentally. So imagine you watch a spaceship passing you at very high speed. What you notice is that the clock appears to run slow. For example, if the spaceship is moving past at half the speed of light, then you see each tick on its clock taking 1.15 seconds. If the spaceship goes past you at 99% of the speed of light, then each tick on his clock takes 7 seconds. What's really amazing, though, is that when you talk to the person on the spacecraft, they'll report that your clock is the one that's running slow. In other words, it doesn't matter who's doing the moving. That goes back to the first idea we talked about before. The laws of physics are the same no matter how fast you're moving. So for the person in the spacecraft, they're the one standing still, and you, and maybe the rest of the universe, is going past them at high speed. So of course, they'll see your clock as being the slow one. As strange as this is, most of us have depended on it at some time. The GPS system relies on very accurate clocks in orbit around the Earth. Because they're moving relative to us, these clocks go slower than clocks on the ground, as observed by us. If the folks who made the GPS system didn't correct for this, the location measurements would be out by hundreds of kilometers in a matter of weeks. When we look at distance, we also see strange effects in relativity. When a spaceship goes past you at high speed, its length gets shorter in the direction of motion. For example, if it starts out at 1 meter length, then once it's moving at 1/10 the speed of light, it will be just half a centimeter shorter in the direction of motion. If it's traveling at half the speed of light, then it's 13% shorter than when it was stationary. Notice that this is only in the direction of motion. So if the spaceship started out spherical, it will be slightly flattened in one direction. Finally, if it's going at 99% of the speed of light, it will be only 14% of its original length. Once again, the person in the spaceship doesn't see their shape as any different. Instead, they see you and everything around you as much shorter in the direction of motion. Once we've changed something as fundamental as time and distance, a whole list of other things change as well. The first of these is mass. It turns out that your mass goes up as you approach the speed of light. If you could reach the speed of light, your mass would be infinite. Of course, as your mass goes up, it takes more force to make you accelerate any more. This is one reason it's impossible to go at the speed of light. It would take an infinite amount of force to reach this speed. Another side effect of special relativity is magnetism. In fact, many physics students first run into special relativity in their electricity and magnetism course. It turns out that if you apply the equations that describe special relativity to the equations that describe a moving electric charge, an additional force appears as a result. This force exactly matches the properties of magnetic fields. Another effect produced by relativity is the distorted view you get of objects moving past you at very high speeds. This is caused by the changing length scales, along with changes in the wavelengths of light you see at high speed. Click on the link to see a series of animations showing what it would look like to travel at close to the speed of light. Finally, we have the equivalence of mass and energy. As we've already seen, matter can be converted directly into energy, and in fact, the reverse is also true. Under the right circumstances, energy can be converted into matter. A small amount of matter can be used to produce a huge amount of energy. As we'll calculate in the next chapter, there's enough mass available in the sun's core to keep it shining just as bright as it is now for a total of 10 billion years. Since our solar system is just a little under 5 billion years old, that suggests that the sun is currently almost halfway through its life. By the way, after Einstein published his special theory of relativity that predicted all of this, the folks in the patent office recognized that he was pretty hot stuff, so they promoted him to patent clerk second class. He didn't stay there much longer.
The conversion of matter into energy is what makes nuclear fusion possible. The nuclear in the name refers to the nuclei of atoms, the protons and neutrons at the centers. In fusion, small atomic nuclei are combined together to produce something larger. In the fusion reactions that power stars like our sun, 4 hydrogen nuclei, or protons, are combined to produce one helium nucleus. Of course, to make fusion happen, nuclei have to collide and merge together. Since they contain positively charged protons, they have to hit each other incredibly fast to overcome the repulsion of their positive charges. Fusion requires temperatures so high that only the sun's core is sufficiently hot. The reason this fusion reaction produces energy is because the product, the helium, has slightly less mass than the 4 hydrogens that went into it. In other words, some tiny amount of mass has gone missing in this reaction, and the missing mass has been turned into energy. If we looked in detail at the sun's fusion reaction, we'd see that it takes multiple steps because the protons don't come together 4 at once, but rather in pairs. For that reason, it's called the proton-proton chain. Besides helium, other particles are produced in the reaction: gamma-ray photons, positrons, and neutrinos. A positron is a form of antimatter, which is like ordinary matter, except that the electric charges are reversed. So a positron is a positively charged electron. The positron will hit an electron, and they will both get turned into energy. A neutrino is an uncharged particle that carries energy, but is almost massless and practically non-interacting. It will come straight out of the sun unchanged, without interacting with the sun's outer layers. We talked about neutrino detectors in the chapter on telescopes. So we see that fusion energy comes out in several different forms: the kinetic energy of the moving helium particle after the reaction, light in the form of a gamma-ray photon, and the energy of the positrons and neutrinos. The important thing to remember, though, is the net effect. 4 protons go into the reaction, and they produce one helium nucleus plus energy.
So what holds the nucleus of an atom together? All those positive charges from the protons are repelling each other, so they should be trying to tear the nucleus apart. Fortunately, there's another force that's important here, and it's called the strong nuclear force. This is a very short-range force. It drops off to almost nothing in just 10 to the minus 14 meters, or about the size of an atomic nucleus. Both protons and neutrons exert the strong force. Since the neutrons don't have any electric charges, putting in lots of neutrons provides more strong force to help hold the nucleus together. That's why all stable elements heavier than hydrogen have as many neutrons as protons, and as you go further down the periodic table, the number of neutrons needed to hold the nucleus together has to grow even faster. This balance between the strong force holding the atom together and the electric force trying to pull it apart also helps explain nuclear fission. When the two forces are nearly balanced, a nucleus can spontaneously split, breaking into 2 smaller parts. Now that we've seen the processes that govern the sun's structure, try predicting how the sun would change if it had a higher mass. You'll have to look at how the temperature would have to change to provide enough pressure to hold up the mass. Then you should think about what the change in temperature would do to the rate at which the sun generates energy through nuclear fusion. Finally, you should look at how the change in fusion rate affects the amount of light the sun generates. Of course, you need to explain your answers to these questions. And remember, these aren't research questions. I'm trying to help you see how to think through the processes inside a star.